Hello and welcome to today's webinar. My name is Chris Kellen and I'm the Director of Geotechnical Analysis for GeoStudio here at Sequent. In this webinar, we will conduct an in-depth exploration of analyzing retrogressive landslides in Slope W and Slope 3D. The overarching goal is to demonstrate the features available in GeoStudio to model this type of failure mechanism. Retrogressive landslides, prevalent in regions with sensitive clays or glaciated terrains, exhibit unique lateral spreading and flow-like movements. As shown in the diagram on the right, the retrogression can span extensive distances, sometimes reaching hundreds of meters upslope. These landslides can enter dormant phases, only to be reactivated by minor fluctuations in pore water pressure or erosional processes. Understanding the strength anisotropy is crucial for analyzing the stability of such landslides, especially in a three-dimensional framework. Today, we will demonstrate the application of weak surfaces and anisotropic surfaces within GeoStudio to provide insights into the analysis of retrogressive landslides and demonstrate how these two features are used to capture retrogressive translational types of failures. Our case study comes to us courtesy of Clifton Engineering Group. The authors, John Osbach, Ellen Kelly, and Wayne Clifton, presented a paper at the 2023 Canadian Geotechnical Conference entitled The Borden Bridge: Remedial Design for a Large-Scale Deep-Seated Landslide. For the purpose of this demonstration, I'm only going to use the geometry and geology from the case study, and I'm not going to try and recreate the more sophisticated analyses found in the paper. Before getting started, I also want to extend a special thanks to the Ministry of Highways in Saskatchewan for sharing the site data and reports to make this webinar possible. Sask Highways has been a strong supporter of geotechnical research for many decades, working closely with academia and industry to support excellence in the field. The site is located on the east bank of a river valley that was formed through post-glacial meltwater erosion over thousands of years. As the meltwater carved through the glacial till, it destabilized the shale layers, resulting in valley wall instability. The valley walls experienced large-scale, deep-seated retrogressive landslides, a common phenomena in regions with clay shale. Referring to the bottom right diagram, the local stratigraphy consists of several distinct layers. First, there's the bedrock clay shale. This is overlain by a disturbed clay shale, followed by glacial till deposited over multiple glaciations. The glacial activity caused significant shearing and thrusting of the upper shale layers, which is reflected in the undulating surface of the shale in the cross-section. Finally, stratified drift resulted from alluvial deposition throughout the river's existence. The red material on the cross-section represents the shear zone at the interface between the intact bedrock and the overlying disturbed shale. As noted, these landslides are common in river valleys eroded into clay shale. Their key features include relatively flat valley wall slopes, composite failure surfaces, and a horizontal shear zone. The material properties that you'll see in the following analyses are taken directly from the author's paper and were determined from a combination of laboratory testing and back analysis. In order to capture the translational mode of failure, we will use the weak surface and anisotropic surface in GeoStudio. Weak surfaces can be used in both 2D and 3D analyses to represent a weak zone in soil or rock. A weak surface could be used, for example, to represent the strength of a single discontinuity, a shear zone at residual strength, or an interface along a soil and geomembrane. The use of a single weak surface is similar to using the impenetrable material model in slope W. However, it differs in that a unique material is associated with the surface. Furthermore, multiple weak surfaces can be defined in a single analysis. Weak surfaces are defined using a polyline in 2D and a background mesh in 3D. Referring to the diagram on the right, a trial slip surface that intersects the weak surface is truncated. The topmost weak surface governs in the event that there are more than one. The strength definition of columns intersected by the weak surface is defined by the material associated with the weak surface. Weak surfaces should ideally extend across the domain to mitigate the generation of poorly shaped slip surfaces. Any slip surface in 2D or 3D that has a stair-step shape is deemed inadmissible. Unlike weak surfaces, the anisotropic surface does not impose a direct control on the shape of the slip surface. Anisotropic surfaces are defined using a polyline in 2D or a background mesh in 3D. The input properties of the anisotropic surface include a base material representing the intact soil or rock matrix, and a material representing the discontinuity. We must also define two angle ranges, A and B. The A and B parameters associated with each anisotropic surface are angular tolerances around the discontinuity that control the transition of shear strength from the anisotropic material into the intact material. The stability solver calculates the shear strength based on the angle between the column base and the anisotropic feature. If that angle is within the A range, the discontinuity shear strength is used. Outside the B range, the shear strength of the base material is used. For angles in between A and B, the shear strength is computed based on a linear interpolation. With that stated, let's get into the demonstration. I'm going to start this demonstration in Leapfrog Works. Leapfrog is Sequent's geological modeling software. We've done a number of webinars that show the workflow between GeoStudio and Plaxis and Leapfrog. For this particular problem, Clifton Engineering Group provided us with a number of data sets. First off, we have the topography shown on the screen here. Note the very shallow slope angle outside the river valley. Next, we have a number of boreholes for the site, which I can drag onto the scene to reveal the geology. Notice that I do not have the intact shale unit in these boreholes. We were also provided with a number of surfaces, including the bedrock surface, an intact shale surface, shear zone surface, and the original ground surface topography data. I then used all of this data to inform a geological model. Okay, so this is the final GM, or geological model, that we're going to use for 2D and 3D analysis. In order to create a 2D geometry, I generated section AA at the location shown on screen. With this model complete, I then published to Sequence Central. And at that point, I'm now going to switch over to GeoStudio. The first step in any numerical analysis is to create the geometry. I'm going to click on Define Project and add a new 3D geometry to this GeoStudio project. Within the geometry editor, I'm going to click on Import and bring in a 2D section from Sequence Central. Step 1 is to select the central server, then the project, and then finally the object that we wish to import. GeoStudio has a different Cartesian coordinate system than Leapfrog, and so I'm going to remap the axes, where the plus Z axis in Leapfrog is the upwards Y axis in GeoStudio, and the plus Y in Leapfrog is our negative Z, which is north facing. And then finally, I'll hit the adjust base point to bring the cross section closer to the origin. With that done, I'll hit OK, and I'll save the transformation template. Now we have our 2D section sitting in three-dimensional space. I will then right-click on section AA and generate a 2D geometry in GeoStudio. With the geometry now created, I'm going to turn off the region labels and point labels, and then shut off the points. On this geometry, I'll go back to Define Project or right-click on the geometry, and I'm going to add a slope W limit equilibrium analysis. I'll click here and rename this 2D stability. Clicking on Define Project again, I'm going to set the pore water pressure conditions to come from a piezometric surface. I'll then close this dialog box and draw my entry and exit zones. Okay. Next, I need to define the piezometric surface. For convenience, I have the XY coordinates of the piezometric line in a spreadsheet. So I'm just going to move off screen here, grab the data from Excel, copy it onto the clipboard, come back to GeoStudio, go to the Define Pore Water Pressure. We'll add a new piezometric surface, and then I'll right-click and paste the points in. And then this piezometric surface applies to all materials. So these are all flagged as yes under the applied category. With that done, I'll now close, and we'll have a quick look at the material properties. The greenish material is our drift with a friction angle of 25 and a cohesion of 7. The red is the disturbed shale with a friction angle of 6.5. And then we have our intact shale, which has been designated impenetrable. The shale at the interface is the material that has a friction angle of 5.4 degrees down at the lowest residual value. For this first analysis, A, I'm going to use the weak surface. We have an icon up in the menu bar called Draw Weak Surfaces, also found under the menu, under Surfaces. So Draw Weak Surface. I'm going to go over and turn the viewpoints on, and then now we'll add a new weak surface and associate this low strength material with this surface. Next, I'll go to the Draw command, and starting over somewhere on the left, near the interface or just above it, I'll click, and then I'll begin to move my way across the geometry. Don't have to be too accurate here. And then I'll just carry this over to the edge of the domain. Okay, then I'll click Done. and I'll zoom back out to the extents of the domain and hit the Solve button. Okay, as anticipated, the factor of safety is close to 1. In this case, it's around 0.96. And notice that the slip surface is truncated down at this weak layer. Now, recall that I assigned an impenetrable material model to this underlying dark gray shell. If I come back to Define, and we go to Define Materials, click on the intact shell, and switch this to, say, more Coulomb with 5 kPa and 36 degrees friction angle, just making some numbers up here, and then resolve, we'll achieve the exact same result. Because keep in mind that the weak surface causes the slip surface to be truncated, and then we trace along and exit back along the arc of the slip surface. If I click on Draw Graph, add a graph, rename it friction angle, change this from strength to material properties and friction angle versus column number, we see that the friction angle drops down to 5 degrees along the weak layer as we would expect. I'm now going to repeat this analysis using the anisotropic surface. First, I'll click on Define Project, and I'm going to rename this Weak Surface. Then, I'm going to add a clone of the analysis, rename it Be Anisotropic Surface. The next step is to go to Define Surfaces, Weak Surface, and I'm going to delete the weak surface that I've defined from Analysis A. Then I'll go to Define or Draw Surfaces, Anisotropic Surface. Now, just like a weak surface, we add one. And then in this case, we select the intact base material, which is the disturbed shell, and then the anisotropic material, which is the blue one. So far, everything is very similar to a weak surface. However, on the Properties tab, we now have to enter in that angle range for A and B, as I discussed on the slide, and then the search mode controls how we raycast to find the anisotropic surface from the base of the column. The default is closest distance. Okay, with that done, I'll now go into the draw mode, and just like the weak surface, I'm going to trace along the bedrock. Now, what's different here is that unlike the weak surface, I could actually draw this pretty much anywhere in space, and I'd get the same result. Because as noted, we search for this surface from the base of each column and then conduct the comparison between the base of the column and the angle of the anisotropic surface. Okay, in definition view, shutting off these points, you'll notice that the weak surface has a dashed line with a dot, and the anisotropic surface has a double dot. So there is a visual indicator that these two are different. Okay, next I'm going to solve this analysis. The factor of safety is 1, and if I zoom back out here, we noticed one key thing. The slip surface shape is circular. As I noted in the PowerPoint, the anisotropic surface does not impose a control on the shape of the slip surface, which is what the weak surface does, because here we've truncated all the columns, whereas here we're only altering the strength at the base of a column that is within that angle tolerance to the anisotropic surface. If I click on Draw Graph and look at the friction angle, we see that only a handful of columns right near this section of the sliding mass right here had a friction angle reduced down to 5 degrees. It's for that reason that optimization is important when dealing with these type of surfaces. I'll go back to the Define project, click on Slip Surface, and turn on optimization. The optimization will work to find a slip surface shape that produces a lower factor of safety. With that on, I'll now resolve. In results view, we see that the factor of safety dropped to 0.92, but more importantly, the slip surface shape has changed dramatically and is more in keeping with analysis A, in that it has a translational component. Clicking on Draw Graph, we now see that all of the columns from about here, where my mouse is hovering, over to this exit point right here, have a friction angle down at 5 degrees. Okay, now that we've explored anisotropic and weak surfaces in 2D, let's now go and recreate this analysis in 3D. The first thing I'm going to do is click back on the 3D geometry. I'm going to right-click and add a Slope 3D analysis. Notice that our section AA is still sitting here in three-dimensional space. Just like we brought in the 2D section from Sequence Central, I'm going to do the same thing for the 3D geometry. Clicking on the Import button, and then import geological model volumes from Central. Once again, selecting the Central server, the project, and then the geological model. I'll hit OK, and then let GeoStudio process the meshes. Just like the cross-section, we can see that some remapping is done, needs to be done, but I'm just going to simply use the transformation template that I had stored for the 2D section. With that complete, I'll hit OK, and once again let the final import stage process. And now the geometry and materials have been brought in. Just as a quick, crude comparison, note that switching over to Leapfrog and switching the transparency to full, we see that the same model that we had in Leapfrog with the mesh shown here is now inside of GeoStudio. Next, I'm going to click on Import Background Mesh. You'll recall that in Leapfrog, we had a surface for the water table, and I published that surface up to Sequence Central. And so I'll bring it in the same manner as a geological model. Okay, there's the water surface. I'll hit OK. Then we'll transform it and hit OK. Now the reason I need this mesh in here is because I'm going to use it to define the piezometric surface. If I click on Define Project, I'll set the pore water pressure conditions to piezometric surface in the same manner that we do for 2D. I'll close this, and note under the Geometry Explorer, we now have a background mesh called Water Surface. I'm going to change the opacity to 0.2, and then now I'm going to go to Define Pore Water Pressure, and instead of drawing a piezometric surface, I'm going to add one and select the appropriate background mesh. Hit OK. Just like in 2D, we want this to apply to all materials, and then I can close this dialog box. Now that we have the geometry, pore water pressures, and materials defined, I'm going to click on Define Project, Slip Surface, and change from entry and exit to the nature-inspired cuckoo search. Now I'll close this dialog box. And actually, I'm going to quickly go back there and rename this to a 3D weak surface. Now, just like we did in 2D with our weak surface defined in a polyline, in 3D, we need to define the weak surface via a background mesh with the exact same workflow that I just followed for the piezometric surface. Click on Define, Surfaces, and Weak Surface. Now, before I do that, I need to have a background mesh representing that contact. So once again, I'm going to import a background mesh from Sequence Central and remind you that over in the geological model, we have all the contact surfaces and output volumes for this geological model. So there's the contact for the intact shale and disturbed shale. Coming back to GeoStudio, I will then go to the server, into the project, and this time select the mesh for the contact surfaces, and in this case I need that surface between the intact shale and the disturbed shale. Hit OK. Transform the surface and hit OK. Now under the background meshes in the Design Explorer, we now have background 2, intact shale, disturbed shale, contact. Now it's hard to see because it only covers the size of the domain. If I go up to down to the geological models and just change the opacity to 0.1, we can now see that background mesh floating in space. Next, I will go to Define, Surfaces, Weak Surface, Add One, and I will select our new contact, hit OK, and change the material to our residual strength. I'll hit Close, come over here, right-click, clone this 3D analysis, rename it B, anisotropic surface. Come back to Define. Just like in 2D, I need to get rid of the weak surface. Close, and then go to Define, anisotropic surfaces. Add, select our background mesh, and then once again, associate the intact strength, the weak or anisotropic material strength, and enter in the A and B ranges. In the interest of time, I've now switched over to a completed file. We've walked through the steps of using background meshes to define the piezometric surface, the weak surface in the analysis that I'm clicked on, and the anisotropic surface in analysis B. I've also added a third analysis to the 3D stack here called Optimize to optimize the critical slip surface of this analysis right here. If I click on Define Project, we see that analysis A is using Morgenstern Price, and we're searching using the nature-inspired cuckoo algorithm. The same is true for our second 3D analysis. And then finally, I set up a parent-child relationship where I added this child analysis and then set the slip surface search option to come from the parent. Then I toggle on Optimize Critical Slip Surface. In this scenario then, where you are only optimizing the most critical slip surface, not all slip surfaces in the search. With that done, I can close this dialog box. The next step that I did was to mesh the domain. Now, under the Generate Mesh dialog box, we note that we are meshing the geometry and we are creating columns for the Slope 3D solver. The volume mesh in the upper portion of the dialog box creates a finite element like mesh that we use to contour data on. So for example, so that we can view pore water pressures spatially across the domain. We also use that mesh to look up or compute values at the base of columns. So I won't hit OK here since it's already meshed, but I will flip over to Mesh View just to show you both the volume mesh. You can see in the light gray pattern here that we have tetrahedral elements, domain. And I can also, up along our view preferences here, I can turn on the ground surface and also turn on the columns. By inspection, we can state confidently that there's enough columns or enough refinement in the columns spacing that we'll get adequate coverage for a typical size slip surface. I'm going to turn off the ground surface and the grid, switch back to geometry, and then we'll go and look at some results. So starting with the weak surface analysis, remember that we had a factor of safety of 0.964 in 2D, and the slip surface is truncated by our weak surface. The same is true in 3D. So clicking on Analysis A here in Results View, the factor of safety is slightly higher at 1.1, and that occurs because of the edge effects along this portion of the sliding mass. I'm currently looking at the critical slip surface, and just like in 2D, I can click on any other slip surface. I just have to let it load a little bit and see the factor of safety and the critical shape. I'll select the Auto Select Critical to go back to our lowest factor of safety. And note that I'm plotting contours of effective normal stress on the columns. In Slope 3D, if we click on Draw Contours, we now have contours for the domain and column contours. And so in this case right here, we have 3 added, including water pressure, effective normal, and base material color. Close this dialog box. And so we can plot water pressure just on the columns. We could also plot water total head on the entire domain. Okay, so again, that's why we need that finite element mesh on our geometry. Okay, for demonstration purposes, I'm going to set this to none, and we'll switch this back to effective normal stresses for the contours. I'm also going to click on our pore water pressure dropdown in the Geometry Explorer, and note that I can toggle off the ponded water or the surcharge load. So just for visibility, I'm going to shut off that water surcharge load, and we'll only see the ponding. Okay, next I'm going to click on Draw a Graph. I'll add a graph and call it a friction angle. And then from the drop-down, I'll switch this to Material Properties and Friction Angle. We can see clearly that there are a number of columns that intersect the weak layer. And so just like in 2D, they've obtained a friction value of 5 degrees. I'm also going to add another graph in here called Analysis B to look at factor of safety versus X lambda. So under the convergence data, we want factor of safety versus X lambda. Now notice that if I look in top view, the sliding direction is fairly aligned with the x-axis. Okay, so this tells us that the factor of safety with respect to x equilibrium was very insensitive to lambda. I'll clone this graph and rename to C factor of safety versus Z lambda. And then I'll change these drop downs to Z lambda. In the Z direction, we now see that there was some variability. So we have our dark purple line here, which is moment equilibrium, and the blue, which is force equilibrium. The converged lambda was at around 0.02, producing a factor of safety of 1.09. Okay, and then finally, I'm going to clone this one more time, rename it D, and call it factor of safety versus sliding direction. Okay, and we see that the sliding direction for convergence, where the factor of safety moment force in the x equals factor of safety moment force in the z, our sliding direction was 251.7 degrees. Okay, so from a top-down view, north is 0, and so 90, 180, 270 is west, so 281 was the critical direction. We can also see that information by going to view sliding mass, and sorry, I misspoke there. The sliding direction is 252 degrees. Okay, with that done, I'm now going to rotate into a side view and zoom in and change the transparency of these three geological model volumes to 0.2, just to demonstrate that in the same manner that the weak surface caused translational mode of failure in 2D, we see the exact same behavior in 3D, in that our background mesh, which serves as our weak surface, acts to truncate the ellipsoid, creating this fairly flat bottom in shape. In general, then, we conclude that the 2D and 3D factor of safety are for all intents equal. Okay, now moving to the anisotropic surface condition, analysis B, we note that the factor of safety is now 1.2. Just like in our 2D example, the factor of safety was 0.964, and the unoptimized factor of safety using an anisotropic surface was 1.03. So slightly higher, and the reason, of course, is that it's circular shape. And in the case of 2D, we needed to optimize the critical, so that's the slip surface right here. We needed to optimize in order to get a translational mode of failure. The same is true in 3D, slightly higher factor of safety with that elliptical shape. We see 1.2, and the base of the sliding surface is just slightly above that contact between the disturbed shale and the intact shale. Then when we go to optimize this surface, we see the factor of safety drop somewhat marginally, but the slip surface shape now adopts a more translational retrogressive mode of failure. In short, then, both the 2D and 3D analysis capture the key mode of failure for this type of problem. In engineering practice, back analysis is frequently used to determine the shear strength characteristics of the anisotropy governing failure. Retrogressive landslides, in particular, are challenging because of their translational mode of failure. A 3D analysis can shed light on key mechanisms, as well as capturing the large lateral spread of the sliding mass. In this webinar, we demonstrated how background meshes are used in Slope 3D to define piezometric surfaces, weak surfaces, and anisotropic surfaces. Weak surfaces impose a direct control on the shape of the ellipsoid slip surface in both 2D and 3D, truncating the slip surface at the contact. Anisotropic surfaces, on the other hand, do not affect the shape directly, The strength at the base of each column assumes the strength of the weak material only if the column base, dip, and dip direction are within tolerance of the dip and dip direction of the anisotropic surface. Consequently, it is very useful to use optimization to allow the slip surface to evolve naturally, following the shape of the anisotropy and producing a lower factor of safety. Thanks for joining us for today's webinar.